Hello, today we are going to talk about the configuration of a gas chromatograph. While following the order in which the sample analysis proceeds, we are going to check the main parts of a gas chromatography analyzer and going to check the roles and features of each part. A gas chromatograph is a chemical analysis instrument for separating chemicals in a complex organic sample. As the carrier gas transports the analyte molecules through the column, there is adsorption of the analyte molecules onto the column walls in the column to give separation. Since each type of molecule has a different rate of progression, the various components of the analyte mixture are separated as they progress along the column and reach the end of the column at different times. A detector is used to monitor the time at which each component reaches the outlet, and the amount of that component can be determined. Generally, substances are identified by the order in which they elute from the column and by the retention time of the analyte in the column. Gas chromatograph has an injector, getting the sample into the chromatograph through it, and it has its carrier gas source and its temperature control oven. It has a column coated with a stationary phase in which the separation occurs, and it has a detector to catch the signal of the chemical components separated from the original sample. The gas chromatograph is simply a temperature-controlled oven designed to hold and heat the GC column. The carrier gas is used to sweep the injected sample down to the column where the separation occurs, and then out into the detector. Gas chromatography is the process of separating compounds in a mixture by injecting a gaseous or liquid sample into a mobile phase called the carrier gas, and the gas passing through a stationary phase. The mobile phase is usually an inert gas or an unreactive gas such as helium, argon, nitrogen, or hydrogen. The choice of carrier gas is important. Helium is the most efficient and provides the best separation if flow rates are optimized. Helium is non-flammable and works with a greater number of detectors. Therefore, helium is the most common carrier gas used. The column inlet provides the means to introduce a sample into a continuous flow of carrier gas. The inlet is a piece of hardware attached to the column head. The injector may be as simple as a septum port on top of the gas chromatograph through which a sample is injected using a syringe. If a solvent matrix has to be vaporized and partially removed, a split-splitless injector is used. Adsorbed samples are introduced using either an external desorption apparatus such as a Purge Trap system or are dissolved in the injector. Sample is introduced into a heated small chamber via a syringe through a septum. The heat facilitates volatilization of the sample and sample matrix. The carrier gas then either sweeps the entirety or a portion of the sample into the column. In split mode, a part of the sample carrier gas mixture in the injection chamber is exhausted through the split vent. A split injection is preferred when working with samples with high analyte concentrations. The real chromatographic analysis starts with the introduction of the sample onto the column. The stationary phase is a microscopic layer of viscous liquid on a surface of metal tubing called a column. The function of the stationary phase in the column is to separate different components, causing each one to exit the column at a different time. Other parameters that can be used to alter the order or time of retention are the carrier gas flow rate, column length, and temperature. The choice of a column depends on the sample. The main chemical attribute regarded when choosing a column is the polarity of the mixture. For functional groups can play a large part in column selection. The polarity of the sample must closely match the polarity of the column stationary phase to increase resolution and separation while reducing runtime. The separation and runtime also depend on the film thickness of the stationary phase, the column diameter, and the column length. The column in a GC are contained in an oven, the temperature of which is precisely controlled electronically. The rate at which a sample passes through the column is directly proportional to the temperature of the column. The higher the column temperature, the faster the sample moves through the column. However, the faster a sample moves through the column, the less it interacts with the stationary phase, and the less the analytes are separated. In general, the column temperature is selected to compromise the length of the analysis and the level of separation. If we increase the column temperature during the analysis, it allows analytes that elute early in the analysis to separate adequately, while shortening the time it takes for late eluting analytes to pass through the column. A detector is used to monitor the time and the amount of the separated components. The eluent coming off the column is monitored by a detector. Substances are identified by the order in which they elute from the column and by the retention time of the analyte in the column. Chromatographic data is presented as a graph of detector response against retention time, which is called a chromatogram. This provides a spectrum of peaks for a sample representing the analytes present in a sample, eluting from the column at different times. Retention time can be used to identify analytes if the method conditions are constant. Also, the pattern of peaks will be constant for a sample under constant conditions and can identify complex mixtures of analytes. The area under a peak is proportional to the amount of analyte present in the chromatogram. By calculating the area of the peak using the mathematical function of integration, the concentration of an analyte in the original sample can be determined. That's all I want to say today. Thank you for watching. See you next time.